This is the Prelab for Experiment 2, Simple and Fractional Distillation. In the first experiment of the semester, you carried out a simple distillation of a hydrocarbon unknown. You did this for two reasons. First, to separate the compound from any impurities, and secondly, to determine the boiling point of your compound. That simple distillation could be used because the compound you started with was 96 to 97% pure to begin with. And the impurities you were separating it from had boiling points that were either much, much higher or much, much lower than your unknown, more than 60 or 70 degrees different. But what if you had not started with a nearly pure compound, but rather a mixture of compounds? And what if those compounds had boiling points that differed by less than 60 degrees or so? Well, that simple distillation would not have separated the compounds, but something called a fractional distillation could have. In this presentation, I'll cover the Prelab assignment, safety information, the goals of the experiment and the methods that will be used to achieve them, background information about distillation and how it can separate a mixture, and how a fractional distillation differs from a simple distillation, some specific information about conducting the experiment, how to clean up at the end of the experiment, and some pointers on completing your analysis. Your Prelab for this experiment consists of reading and reviewing the assigned sections from Techniques in Organic Chemistry and preparing your notebook using the investigative format. If you have read the procedure, you'll note that you'll be collecting a lot of data in this experiment. For the distillation alone, you need to record about 50 data points, so set aside space in your notebook so you can do this in an orderly fashion. The safety information you note for this experiment is that cyclohexane is flammable and irritating. Toluene is flammable and toxic. So don't handle these compounds near open flames, and be careful around other heat sources such as the heating mantle you use for the distillation. Prevent eye, skin, and clothing contact, and avoid inhaling the vapors or ingesting the compounds. The goal of this experiment is to compare the ability of a simple distillation to separate a mixture of cyclohexane and toluene to that of a fractional distillation of the same mixture. Since we've supplied you with the necessary data from a simple distillation of cyclohexane and toluene, you will need to carry out the fractional distillation. During that distillation, you will record the boiling temperature as a function of volume of distillate collected. Since this will be done on a micro scale, volume will be measured in drops. You'll collect the drops in portions in test tubes, 10 drops to a tube. These portions are called fractions of the distillate. After you've finished distilling the mixture, you'll measure the refractive index of each fraction you collected. The boiling point data and the refractive index data can be used to estimate the composition of the distillate at different points in the distillations. So in your analysis, you'll compare the data given in lab manual to the simple distillation. You'll compare the data given in the lab manual for the simple distillation to your data for the fractional distillation. So, how can a distillation separate a mixture? Let's consider the mixture of cyclohexane and toluene you will start with. Importantly, these liquids are miscible, meaning they form a homogeneous mixture when they're added together. This discussion of distillation only applies to that type of mixture. Mixtures of immiscible liquids like oil and water behave differently. Thinking about the cyclohexane-toluene mixture, we can describe the vapor pressure above the mixture using Dalton's law, whereby the total vapor pressure is simply the sum of the partial pressures of cyclohexane and toluene above the liquid. It can be shown that at a particular temperature, the partial pressure of a component can be expressed as the product of two terms. The component's mole fraction in the liquid below the vapor, and the vapor pressure that the compound would exert at the temperature on its own. So the mole fraction of cyclohexane in the liquid can be expressed as X with a little subscript C for cyclohexane, And the vapor pressure that cyclohexane would exert at that pressure in its pure form can be expressed as P with the superscript 0 and the subscript C. We can express the same terms for toluene. If we substitute these expressions for both cyclohexane and toluene into Dalton's law, it gives an expression for the total vapor pressure known as Raoults' law, now expressed in terms of mole fraction in the liquid and the partial pressures of the pure components. To understand what Raoults' law tells us, we first need to think more about the vapor pressures of the components of our mixture. In general, vapor pressure is inversely proportional to boiling point. In this case, cyclohexane has a lower boiling point than toluene, and therefore a correspondingly higher vapor pressure. This is evidenced in their behaviors, their volatilities. Cyclohexane has a relatively low boiling point and will evaporate relatively quickly from an open container. On the other hand, toluene has a much higher boiling point and is much slower to evaporate. Importantly, this difference in vapor pressure is true at all temperatures. Cyclohexane has a higher vapor pressure than toluene at room temperature, and it does so at boiling temperature of a mixture of cyclohexane and toluene. So, what does Raoults' law tell us will happen if we distill a mixture of cyclohexane and toluene? Since we're starting this experiment with a 50-50 mixture, the mole fraction of cyclohexane in the liquid is equal to the mole fraction of toluene in the liquid. And as I just described, the vapor pressure of cyclohexane is greater than the vapor pressure of toluene above the liquid at all temperatures. So it follows that the product of mole fraction and vapor pressure for cyclohexane will be greater than that for toluene. Now, if you recall, Raoults' law is just a different way of expressing Dalton's law, which is in terms of partial pressures. So we can conclude that this predicts that in the vapor above the liquid, which is a 50-50 mixture, the partial pressures of cyclohexane and toluene will be different, and the partial pressure of cyclohexane will be greater than the partial pressure of toluene. It also follows from Avogadro's law that the number of moles of cyclohexane in the vapor will be greater than the number of moles of toluene. So ultimately, we can conclude that even though the liquid is equal parts cyclohexane and toluene, the vapor above it contains more cyclohexane than it does toluene because of their different volatilities. This is true whether the liquid is sitting at room temperature or whether we heat it to its boiling point. The vapor will be enriched in cyclohexane relative to toluene because cyclohexane is more volatile than toluene. So this phenomenon will affect the boiling point of a mixture of cyclohexane and toluene. In fact, we can plot boiling point as a function of composition. We can define composition of our cyclohexane-toluene mixture simply in terms of percent toluene. So on a graph of this sort, the boiling point of pure cyclohexane, which is 81 degrees, will appear on the far left of our plot, 0% toluene. And the boiling point of pure toluene, 100% toluene, which is 110 degrees, will appear on the far right of our plot. Because of the difference in vapor pressures, the boiling point of a mixture follows a downward deflected curve rather than a straight line between these points. This curve is called the liquid curve on this plot. We can also show in this plot a so-called vapor curve. This gives the composition of the vapor over the liquid. So here's how we use the plot. If we have a mixture of a particular composition, say 50% toluene like we will use in this experiment, we can draw a vertical line from that point on the composition scale. Its intersection with the liquid curve gives the boiling point of that mixture. Here it appears to be about 91 degrees. If we draw a horizontal line at that boiling point, it will intersect the vapor curve at a point that corresponds to the composition of the vapor. So this graph predicts that the vapor above this 50-50 liquid will be only about 24% toluene and 76% cyclohexane. Remember, cyclohexane is more volatile than toluene. Now imagine that we trap some of that vapor, this 24% toluene, 76% cyclohexane, using a distillation apparatus, and condense it back to a liquid. That liquid will have the same composition as the vapor that it came from, 24% toluene, 76% cyclohexane. Now imagine that we distill that liquid. This graph predicts that it should boil at a temperature closer to 85 degrees, and it'll produce a vapor that is only about 10% toluene. I think you can see that if we repeat this process just a few more times, we would eventually collect some pure cyclohexane. Each of these vaporization condensation steps is called a theoretical plate. And carrying out this iterative process can be accomplished by a simple modification of our distillation apparatus, the addition of something called a fractionating column. Here we see a picture of the apparatus you will use to do the fractional distillation of cyclohexane and toluene. Between the distilling flask and the distilling head, in this region, is placed a column that has been partially filled with stainless steel wool. Other materials can be used to fill the column. All that's required of this material is that it be chemically inert, so it doesn't react with our compounds, and that it be stable to the temperatures of the distillation. We don't want it to melt or anything. And it doesn't completely clog the column. When the liquid in the distilling flask is boiled, vapors from that liquid will climb up the column, condense on the cooler surfaces of the column and the steel wool. Eventually, that condensate in the column will be reheated by hot vapors rising up from below, and it partially re-vaporizes. This newly formed vapor climbs a bit further up the column, and the process repeats. Eventually, the vapor and condensate reach the distilling head, and if a sufficient number of vaporization condensation steps occur, remember we call those theoretical plates, the more volatile compound reaches the condenser in pure form. If we were to monitor the temperature in the distilling head during a simple and a fractional distillation of the same mixture, we can learn something about the vapor that's reaching the condenser. Here we see a plot of that temperature for both a simple and a fractional distillation of a mixture of 25 milliliters of cyclohexane and 25 milliliters of toluene. The simple distillation data shows an incomplete separation. At the very beginning of the distillation, the boiling temperature is around 83 degrees. So if we look at this end of the simple distillation curve, this indicates that the first drops of liquid making it to the condenser aren't pure cyclohexane, which boils at 81 degrees. This higher boiling temperature indicates that it must be mixed with some toluene. We can also see that at the end of the distillation, it never reaches the boiling point of toluene. This indicates even at the end, some cyclohexane remains and is not being separated from the toluene. So the initial and final fractions are enriched, the initial fractions being more cyclohexane than toluene, the final fractions being more toluene than cyclohexane, but they remain mixtures. In contrast, the temperature at the beginning of the fractional distillation is 81 degrees, which is the boiling point of cyclohexane. It remains at that temperature through the first 15 milliliters of the distillation. That means the first 15 milliliters is nearly pure cyclohexane. After that, the temperature rises rapidly and eventually levels out at 110 degrees over the last 15 or 20 milliliters. If one were to collect the distillate from this distillation in, say, 5 milliliter portions, fractions, The first 3 fractions would be cyclohexane, the last 3 or 4 fractions would be toluene, and the middle 3 or 4 fractions would remain a mixture. So a simple distillation is only useful for separating mixtures if there is a great difference in volatility of the components, meaning a boiling point difference greater than 60 or 70 degrees. But on the other hand, a fractional distillation can separate a mixture with much closer boiling points, depending upon the efficiency of the fractionating column. Some tips on conducting the distillation. To give efficient separation, the column has to be properly packed with the steel wool. Too much will clog the column, too little will greatly reduce its efficiency, the number of theoretical plates it produces. It's also important that it be evenly packed from top to bottom. Uneven packing will reduce its efficiency. In the picture you see here, this is a properly packed fractionating column. An even temperature gradient up the column is essential to efficiency, so the column has to be insulated. You'll do this simply by wrapping the column in a little cotton and then surrounding that with a little aluminum foil, such as you see in the picture here. Finally, the procedure calls for heating the mixture until the condensate is just below the side arm of the distilling head and then maintaining that for 5 minutes. This is absolutely essential. If you don't equilibrate properly or long enough, the efficiency of the column will be reduced and your data will look more like a simple distillation than it does like a fractional distillation. Cleaning up. All of the collected fractions and any residue should be placed in the designated waste container. Boiling chips can go into the regular trash. And the glassware can simply be dried and returned to the red kits, and the kits can be replaced to where you got them. For the data analysis, don't forget to attach your graphs and data tables to your lab report. It's very important that you cite specific data, numbers, boiling points, refractive indices, and the differences between them in your answer to question number 1. And finally, be sure to report and discuss any issues that may have affected the quality of your data. In other words, if your data indicates that your fractional distillation wasn't particularly efficient, you should indicate why or that may have happened. Perhaps you noticed that the column wasn't packed properly, or you were having trouble equilibrating the column. Any of those sorts of issues are important to note when you're talking about the quality of your data.